What if the very apple that fell on Newton's head wasn't just a fruit, but a clue to the hidden architecture of the universe? In this episode we peel back the layers of a mind that dared to map the cosmos with nothing but curiosity and a handful of equations. On Christmas Day in 1643, in the modest woolly working village of Woolsthorpe by Colsterworth, a child was born who would later rewrite the rules of nature. Isaac was the only surviving son of a prosperous farmer, but his early years were shadowed by the turmoil of the English Civil War, which left his family financially strained. When his father died before he could speak, young Isaac was sent to live with his maternal grandparents, a stern couple who prized hard work and piety. The farm's quiet fields and the surrounding countryside sparked his curiosity about the motion of objects, from rolling stones to the rhythm of the wind. He attended the local grammar school where he first encountered Euclid's geometry, a study that delighted his analytical mind. Yet, the school was also a place of strict discipline, and Newton learned to channel frustration into solitary contemplation. By the age of 12, he was already known among his peers for his relentless questioning of why things fell the way they did. This early blend of hardship, rustic observation, and rigorous schooling laid the foundation for a mind that would soon challenge the very fabric of scientific thought. In 1661, Newton earned a scholarship to the King's School in Grantham, where he excelled in mathematics and Latin, catching the attention of a local vicar who recommended him to Trinity College, Cambridge. Arriving in Cambridge in 1665, he found a university still reeling from the aftermath of the Great Fire and the lingering effects of the plague. The city was closed, and the college grounds became a sanctuary for scholars seeking refuge from the disease-ridden towns. Newton, isolated from the bustling academic life, turned his attention inward, devouring the works of Descartes, Kepler, and Galileo while beginning his own experiments with prisms and light. He famously split white sunlight into a spectrum, discovering that colors were intrinsic properties of light, not alterations by the prism itself. This revelation sparked a lifelong fascination with optics, leading him to construct the first practical reflecting telescope, later known as the Newtonian. Meanwhile, the plague forced the university to suspend lectures, giving Newton uninterrupted days to develop the mathematical foundations that would become calculus. In letters to his friend John Wickens, he confessed that this period of enforced solitude was the most fruitful of his life, a sentiment that underscores how crisis can incubate brilliance. Legend tells that in the summer of 1666, while walking in the orchard of his family farm, Newton observed an apple fall to the ground, prompting the question that would change humanity's view of the heavens. He wondered whether the force that pulled the apple also governed the motion of the moon, a notion that seemed heretical in an era still dominated by Aristotelian physics. Over the following months, he began to formulate a universal principle, calculating that the same inversia square law could explain both terrestrial and celestial motions. In a notebook dated December 25, 1666, he wrote, "If I have ever made any discovery, it has been owing to my patient perseverance and the fruit of a pure imagination." By the autumn of 1669, he had completed the preliminary equations that later became known as the law of universal gravitation, linking the mass of objects to the distance between them in a precise mathematical relationship. This insight bridged the gap between the heavens and the earth, establishing a single, elegant law that described the motion of planets, comets, and falling apples alike. Newton's contemplation of a simple orchard fruit therefore blossomed into a principle that would dominate physics for 3 centuries. The force of attraction between two masses decreases with the square of the distance. While pondering the motion of planets, Newton realized that existing mathematics could not adequately describe continuously changing quantities such as velocity and acceleration. He invented a new method, which he called the method of fluxions, to handle infinitesimally small changes, laying the groundwork for what we now call calculus. In a series of manuscripts written between 1665 and 1669, he defined derivatives as the ultimate ratios of evanescent quantities and integrals as the inverse operation, allowing him to derive the area under curves and the slopes of tangents with unprecedented precision. His work remained unpublished for many years, partly due to a fierce rivalry with the German mathematician Gottfried Wilhelm Leibniz, who independently discovered similar concepts. The ensuing priority dispute would dominate scientific correspondence for decades, yet the core ideas survived, fundamentally reshaping mathematics. Newton's calculus became the indispensable language for expressing the laws of motion and gravitation, turning qualitative observations into quantitative predictions that could be tested against the heavens. Force equals mass times acceleration, linking motion to applied forces. In 1687, after years of private study and secretive correspondence, Newton presented his magnum opus, the Philosophia Naturalis Principia Mathematica *, to the Royal Society. The work, dedicated to his patron Edmund Halley, unfolded in 3 books, the first laying out the 3 laws of motion, the second applying them to planetary orbits, and the third exploring the motion of fluids and tides. Newton's first law proclaimed that a body in motion remains in uniform motion unless acted upon by a net force, while his second law quantified the relationship between force, mass, and acceleration. The third law introduced the concept of equal and opposite reactions, a principle still central to modern physics. By mathematically proving that Kepler's elliptical orbits could be derived from a universal inversia euro-square force, Newton unified celestial and terrestrial mechanics under one elegant framework. The Principia not only cemented his reputation but also ushered in the Age of Enlightenment, providing a model of rational inquiry that would inspire generations of scientists, engineers, and philosophers. Even as he revolutionized mechanics, Newton continued to explore the nature of light. In 1672, he presented his experiments with prisms to the Royal Society, demonstrating that white light is composed of a spectrum of colors, each refracted at a slightly different angle. This insight contradicted the prevailing belief that colors arose from the modification of a pure white ray. To further his study, he designed the reflecting telescope, which used a curved mirror instead of a lens to gather light, eliminating the chromatic aberration that plagued refracting telescopes of the era. The first prototype, completed in 1668, allowed for clearer and brighter celestial observations, and its design remains the basis for many modern telescopes. Newton's work in optics not only advanced astronomical instrumentation but also deepened humanity's understanding of the fundamental properties of light, paving the way for future breakthroughs in wave theory and quantum mechanics. Beyond his public scientific achievements, Newton devoted much of his later life to alchemy, a pursuit that occupied roughly a third of his written output. He meticulously studied ancient manuscripts, seeking the legendary philosopher's stone and the transmutation of base metals into gold, believing that unlocking nature's hidden forces would complete his understanding of the universe. His alchemical notebooks, filled with cryptic symbols and experiments involving mercury, antimony, and nitric acid, reveal a mind that refused to separate the mystical from the empirical. Simultaneously, he served as warden and later master of the Royal Mint, where he reformed England's coinage, tackled counterfeiting, and introduced rigorous standards that stabilized the economy. These dual roles, secretive alchemist and pragmatic public official, illustrate the complexity of a man whose curiosity knew no boundaries, straddling the line between the Enlightenment's rationalism and the lingering mysticism of the 17th century. The 1690s saw the infamous calculus priority dispute erupt between Newton and the German mathematician Gottfried Wilhelm Leibniz. While Newton had developed his method of fluxions privately, Leibniz published his differential notation in 1684, sparking a fierce debate over who first discovered the infinitesimal calculus. Nationalistic fervor inflamed the controversy, with English and continental scholars taking sides, leading to a bitter exchange of pamphlets and accusations of plagiarism. Newton, now president of the Royal Society, oversaw the publication of the Commercium Epistolicum *, which presented his claims and cast doubt on Leibniz's originality. Despite the acrimony, both mathematicians' notation survived, with Leibniz's dy/dx becoming the standard. The rivalry, though damaging to personal relations, ultimately accelerated the development and dissemination of calculus across Europe, illustrating how competition can spur scientific progress. In 1703, Newton was elected president of the Royal Society, a position he held until his death, guiding the institution through a golden age of scientific inquiry. He presided over landmark experiments, championed the work of emerging scientists, and oversaw the publication of the Philosophical Transactions *, ensuring that rigorous peer review became a cornerstone of scientific communication. During this period, he also received the coveted Copley Medal for his contributions to optics and mechanics. Despite his advancing age and a growing deafness, Newton remained intellectually active, corresponded with continental scholars, and published *Optics* in 1704, a work that emphasized experimental observation over mathematical abstraction. His later writings reflected a cautious humility, acknowledging the limits of human understanding while celebrating the power of reason to unveil nature's secrets. Isaac Newton died on March 20, 1727, at his London home, leaving behind a legacy that would dominate science for centuries. He was buried with honor in Westminster Abbey, a tribute reserved for the nation's most eminent figures. In the years following his death, his *Principia* and *Optics* were reprinted, translated, and studied by every aspiring natural philosopher, cementing his status as a foundational pillar of modern physics. The law of universal gravitation guided the trajectories of early space explorers, while his calculus became the language of engineering, economics, and even biology. Philosophers such as Immanuel Kant and later Albert Einstein cited Newton as a profound influence, with Einstein remarking that Newton's work provided the firmest edifice on which we have built the modern edifice of physics. Newton's integration of mathematics with empirical observation set a methodological template that continues to shape scientific practice today. Even as quantum mechanics and relativity redefined the boundaries of physics in the 20th century, Newtonian mechanics remains the workhorse of everyday engineering. From the design of bridges and automobiles to the flight dynamics of aircraft, engineers still rely on the three laws of motion to predict how objects will behave under forces. Satellite navigation systems, while accounting for relativistic corrections, base their core orbital calculations on Newton's law of universal gravitation. The simplicity and accuracy of his equations at ordinary speeds and scales make them indispensable tools in classrooms, laboratories, and industry worldwide. Newton's legacy, therefore, lives not only in lofty theoretical frameworks but also in the concrete machines and infrastructure that shape contemporary life. Newton once wrote, "If I have seen further, it is by standing on the shoulders of giants, acknowledging the cumulative nature of scientific discovery." His relentless pursuit of understanding, from the falling apple to the behavior of light, exemplifies an unquenchable curiosity that continues to inspire. Today, students across the globe recite his laws, scientists build upon his mathematics, and artists evoke his image as the archetype of the lone thinker. The story of Isaac Newton reminds us that profound insights often arise from simple observations, that rigorous mathematics can translate wonder into law, and that the quest to decode the universe is an everlasting adventure. As we look to the stars and probe the quantum realm, we do so on a foundation he first laid, forever echoing his words, "Nature is pleased with simplicity." Tomorrow we plunge into the electric storm that lit up the 19th century. Michael Faraday, the restless experimenter who turned invisible forces into visible wonder. Will his discoveries of electromagnetism and electrochemistry rewrite everything we think we know about the world? Tune in to find out. Subscribe, and don't miss it.